Hello all, welcome to the Basics.Academy. This is Smart Contract Security, Fundamentals and Auditing, a 5 units, 3 credit course in the BSc Blockchain Technology program. Let's get into it. Lecture 1, Introduction to Smart Contract Security. In Unit 1, we are going to talk about the stakes, the life cycle, and the principles of writing code that guards real money. Always remember, code is law and the law executes with no undo. Why this course exists? Smart contracts move real money and their mistakes are permanent. Let us take a look at some of the most popular hacks which has happened in the past. The DAO hack, which happened in 2016, that led to the split of Ethereum into two different chains, Ethereum and Ethereum Classic. This hack happened because of the re-entrancy bug. Second one is the Ronin bridge hack. In this case, no clever code was used, however, the validator keys were stolen. And at last, we look at Wormhole. This happened because of a single missing signature check that minted tokens from thin air. The minting logic did not have the signature check. Billions of dollars have been lost to exploitable smart contracts. Almost all of it was preventable. That is exactly what auditing is for. This course consists of 5 units. Right now, we are at Introduction to Smart Contract Security. Next, we will cover Secure Solidity Foundations, in which we will discuss message.sender versus transaction.origin, what is visibility, what are function modifiers, and safe errors. Then in Unit 3, we will talk about common smart contract vulnerabilities, citing a few of those: re-entrancy, overflow, access controls, oracles, and front running. Then in Unit 4, we will cover testing and auditing tools. To cite a few of those: Remix, Hardhat, Slither, static analysis, and unit tests. And at last, we will conclude this course with audit reports and ethical practice. The finish line: you will write, review, and present your own mini smart contract audit report. What is a smart contract? The thing we are trying to secure. By definition, a smart contract is a program stored on a blockchain that runs automatically when its conditions are met, with no bank, broker, or intermediary in the middle. However, I want to cite a point over here. The smart contract does not run automatically. The functions in the smart contract are invoked via external transactions. The properties of smart contracts includes they are self-executing, runs itself when triggered. This when triggered part is equal to when we are sending transactions to the smart contract. Deterministic, same input will always give the same result. Transparent, the bytecode is public and verifiable by anyone. Value bearing, it can hold and move funds directly. Let us have a look at the wallet.sol smart contract. This smart contract has a single mapping, a deposit function, and a withdraw function. This looks harmless, isn't it? Hold that thought. We are going to break this later. This smart contract is in line with what exactly happened in the DAO hack. Why smart contracts are uniquely dangerous? There are 5 properties that turn ordinary bugs into catastrophes. First one is immutable. Once you deploy a contract, you cannot patch it. You cannot upgrade it. However, if you have deployed an upgradable smart contract, in that case, you can upgrade the smart contract in case of any bugs. Public, anyone, including attackers, can read the code and state. Value bearing, the contract itself holds the money, it is the target. Contracts can call another contracts. One flaw cascades outward. This exactly happened in case of DAO hack. wherein the attacker contract was able to call the withdraw function of the DAO smart contract, resulting into draining all the funds from within the DAO contract. And it is adversarial. It runs in the most hostile environment in software. Keep a note of it. A missing semicolon is a typo, whereas a missing check is a heist. In case of DAO hack, updating the state after the ETH transfer was dangerous. So that there was a missing check that led to a heist. There are layers of security, and we must know where we are standing. We are standing at the smart contract layer, wherein we audit the code part that includes logic, access control, and funds. The smart contract lifecycle. It begins with the design phase. In the design phase, we identify the threat model before writing even a single line of code. What is a threat model? We go ahead in the time and think of scenarios in which our smart contract is compromised. If the smart contract is compromised, how can we stop the hack? How can we mitigate the risk? Should we add the possible functionality? Should we add the ownable functionality? Should we add access control in our smart contract? All these things are taken into consideration in the design phase. After the design phase, we move to the actual development phase. In development phase, we write our contract code using secure patterns. For example, if you want no reentrancy bugs in your smart contract, it is recommended to follow check effects interactions pattern. Also, it is recommended to not reinvent the wheel, whereas to use trusted libraries wherever possible. One example of such is OpenZeppelin. After the development phase, testing part is the most important. We are advised to perform unit test cases end to end, taking into consideration the edge cases and also integration test cases. The end goal should be to have a code coverage of greater than 95% when you are writing test cases. After phase 3, the smart contract goes into the audit phase. In the audit phase, the contract is handed over to external entities wherein they go through our smart contract line by line and report any bugs or potential issues that may lead to loss of funds. After that, it is the developer's responsibility to take into consideration the audit findings and give the proper fix. Once the smart contract audit phase has cleared, then it moves to the deployment phase. The key note here to keep in mind is deployment is a one-way door. There is no easy undo. After deployment, we go into the monitoring phase wherein we watch, alert, respond and pause depending upon the interaction or the transactions happening in our smart contract. Thing to keep in mind is security is not a final step, it lives at every stage. A bug caught in design costs minutes. The same bug caught after deploy can cost millions because deploy is a one-way door. The reentrancy bug, if it would have been caught in the design phase, would have not led to the DAO hack, but that was skipped and the DAO hack happened. When it comes to auditing, understanding the attack surface is very important. In case of smart contract, what are the different attack surfaces? Let us discuss those one by one. First is contract logic. What if your contract has a reentrancy bug? Now this attack surface is related to logic. Next we have access control, wherein we decide who can call the sensitive functions. Talking about access control, some functions can be invoked by owners, other functions can be invoked by admin. Then we discuss about external calls. Calling untrusted contracts you don't own. In case of DAO hack, there was an attacker contract, the smart contract, which kept on calling the withdraw function. The next one is oracle and price feeds. If your smart contract depends upon oracles, what if the oracle got manipulated? Admin keys and upgrades. It gives centralized powers and upgrade backdoors. This has happened in case of the treat token, wherein the admin keys was still with the older developer, then they rebased the entire treat token. Coming to dependencies, if you are using some library X and that library X has some issues, those bugs will be inherited into your smart contracts. Economic design, flash loans, incentives, and last but not the least, maximum extractable value. Then the last attack surface is front-end and user, wherein the attacker can use activities such as phishing and get malicious approvals from the user and then submit those approvals on-chain. These are the 8 attack surfaces when it comes to smart contract security. Auditing means walking every one of these doors and asking, what if the attacker controls this? So, what if the admin keys are compromised? In that case, what will be the mitigation strategy? In case of access control, what happens if the owner key got compromised? Is there a way wherein we can remove the owner? What if the admin keys are compromised? What if the contract has a re-entrancy bug? Is the smart contract upgradable? What if the contract calling another contract has some fishy code that can again call back into the calling contract? So these all things you must take into consideration before auditing a contract or while auditing a contract. You have to identify all the doors through which the attacker can enter, and then you have to ask the question to yourself, what if the attacker controls this? The answer to that question becomes your audit findings, and that hardens your smart contract code. Why securing dApps matter more than secure applications? Let us compare them side by side. On the left side, we have Web 2, which is a traditional app. Then on the right side, we have smart contract, which is Web 3. In case of Web 2, if something goes wrong, the bank can reverse fraud and issue chargebacks. The bugs can be hot fixed quietly in the next release. The source code is private, but team can freeze accounts and at last support desk to call when it breaks. Whereas in case of smart contract or Web3, transactions are final. There is no undo, no reversal. Once you submit the transaction, it is bound to go through. Deployed code is hard or impossible to patch because of the immutability nature of the code. Third, the code is public. Attackers audit you for free. Fourth, no one can freeze a thief mid-trade. If a hack is happening, a transaction is executing, no one can stop that transaction. Losses hit real user funds and your reputation. On the first slide, we talked about the DAO hack, the Ronin bridge hack, and the Wormhole hack. All those hacks have impacted real user funds. Trust is the whole value proposition. One exploit can end a protocol overnight, and this has happened in the past with many protocols. Same mistake, wildly different consequences. Security isn't a feature of a dApp, it is the product. If you are creating a dApp, security is not a feature for the dApp, that is the product. 3 principles that guide everything. I would request everyone to memorize this because we are going to return to them in every unit. First is of least privilege. Grant the minimum access needed, nothing more. If somebody wants to update a state variable, give them that access, nothing more than that. Fewer people who can pull the lever is equal to fewer ways to break it. Examples are only owner and role-based access. Defense in depth. Never rely on a single control. Never ever do this in case of smart contracts. Layer protections so one failure isn't fatal. Input checks, re-entrancy guard, limits, and monitoring all at once. Checks plus guards plus limits. And at last, fail safe defaults. When something goes wrong, fail closed, not open. Deny by default, revert on doubt, and build a pause or circuit breaker for emergencies. Always make sure that your smart contract has a pause or circuit breaker for emergencies. You never know when you are in need of one such functionality in your smart contract. Secure design is not a trick you apply once. It's a mindset you apply everywhere. We are going to develop that mindset in this course. Let us take a look at all the hacks which has happened in the past. First and foremost is the DAO hack. The root cause for this hack is reentrancy. Then we have polynetwork. What is polynetwork? Polynetwork is a cross-chain interoperability protocol that transfers tokens from one chain to another chain. The reason for this hack was access control. Then we have Ronin bridge. The root cause was stolen keys. Wormhole, root cause signature check. And then Nomad bridge. The root cause was faulty in it. Notice the pattern. These are known named bug classes. They are not unknowable magic. These could have been prevented with a review. In this course, we are here to list down those patterns and what are the mitigations for those patterns. Let us take a look at the few of the case studies of the major hacks that has happened. First and foremost is the DAO hack, the bug that split Ethereum into two. What it was, what was the vulnerability, what was the impact of this, and what was the final lesson from this hack. What it was? First, it was a community investment fund on Ethereum that raised approximately 3.6 million ETH from thousands of contributors. What was the vulnerability? Re-entrancy. The withdraw function sent ETH out before updating the balance. So an attacker re-entered and drained repeatedly. What was the impact? 3.6 million ETH was drained. To recover funds, Ethereum hard forked, creating Ethereum, which is ETH, and Ethereum Classic, which is ETC. What was the lesson? Check effects interactions. Always, always, always update state before any external call. Use re-entrancy guards. The exact pattern in our wallet.sol slide, it's the reason the check effects interaction exists. Then we have the Ronin bridge hack. Again, what it was, what was the vulnerability, what was the impact, and what was the lesson. It was not a code bug, it was a trust bug. The Ronin sidechain bridge powering the Axie Infinity game secured by a set of 9 validator nodes. The vulnerability, access control or key compromise. The attackers obtained 5 of 9 validator private keys, partly via social engineering, a majority, and simply signed off fake withdrawals. They got hold of the validator private keys and started signing off fake withdrawals. What was the impact? Approximately 1,73,600 ETH plus 25.5 million USDC tokens were stolen, totaling to about $625 million. The largest crypto hack at the time, and it went undetected for 6 days. The lesson? Decentralize trust and manage keys ruthlessly. A bridge is only as safe as its signer threshold. Perfect solidity can't save you if the keys that control it are stolen. Least privilege in action. At last we have Wormhole, one missing check, tokens from nothing. So there was a verification step that was skipped. A single verification step that failed open instead of failing safe. Defense in depth would have caught it. But that was not the case. A popular bridge letting assets move between Solana and Ethereum by locking on one side and minting on the other. So Wormhole bridge moves tokens to and fro from Ethereum to Solana and from Solana to Ethereum. What was the vulnerability? Faulty signature verification. The contract failed to properly validate the guardian's signatures. So what happened? The attacker forged approval and minted tokens with no collateral behind it. What was the impact? 1,20,000 wrap teeth, approximately $320 million, were minted from thin air. Jump Crypto replaced the funds to keep the bridge solvent. What is the lesson here? Always validate every input and every signature. Never trust, always verify explicitly. Almost every headline exploit is a known pattern that slipped past review. Unsafe external calls that happened in case of DAO. Reentrancy, talking to untrusted code mid-transaction. Broken access and keys, wrong people can call or keys get stolen. The Ronin bridge hack. Missing validation, inputs and signatures trusted without checking. The wormhole hack. Flawed logic math, overflow rounding, wrong assumptions. This has caused to hacks in many protocols. Centralized trust, upgrade keys and admins that fail open. Example breaches. Economic manipulation, flash loans and oracle price games. In case of decentralized finance. This is why we audit. Not to find magic, but to catch the known patterns humans keep repeating. The key takeaway from our lecture 1 is security is not optional. Contracts are immutable, public and hold value. A bug is permanent and expensive. Audit before the one-way door. What was the one-way door? The deployment phase or step 5. Before deployment, your contract must be audited and reviewed, and all the audit changes must be fixed prior to deploying your contract. 3 North Stars: least privilege, defense in depth, fail-safe defaults. Apply them everywhere when you are developing smart contracts. Hacks are preventable. Billion-dollar exploits trace back to known, named, and teachable patterns. In next lecture, we are going to talk about secure solidity foundations, wherein we will discuss message.sender versus transaction.origin. Then we will talk about visibility specifiers, modifiers, require, assert, revert, and gas basics. That wraps up this session. If it helped, like and subscribe so you don't miss the next one. Questions? Drop them in the comments below. See you in the next lecture.